All right, everybody. Good afternoon. So if you are looking at your notes right now, you will notice that there's a little bit of a change, and the change is this guy right here. So I don't know. In my hurry to improve the notes and add things to them, I posted or pasted the wrong first law. I posted it or pasted the first law for an open system, which is not what we're doing here. We've got a piston cylinder. We're modeling it as a closed system for our ideal Otto cycle. So I did change that. And I also updated that on the guided notes that's on Canvas. Now that probably isn't really help you if you already downloaded it and you're writing on it. So just make sure that you update that formula there. And there's a similar update when we get to the diesel cycle, which is in just a little bit. Okay, so sorry about that. On the struggle bus a bit. Okay. So I think I wrote this yesterday and I probably should have continued, but 1 to 2 for an ideal Otto cycle, which is our very simplified model for our gasoline engine. We've got an isentropic compression followed by a constant volume heat addition. And then we also have isentropic expansion. And then we also have a constant volume heat rejection. I'll put it as blue, Q out. So what I'm going to do is I'm going to go through and I'm going to derive, using the first law applied to a closed system, I'm going to derive the equation that I'm going to use to model each of those processes. So you got 4 processes, 4 times you're applying that first law, but I'm just going to continue to reference the same first law, which is up at the top there. So for the first guy, you've got an isentropic compression. And isentropic, remember isentropic is adiabatic and reversible. So adiabatic is a big one. So I don't have any of this. And it's a compression process. You're putting work into it, right? You do have boundary work, and the volume is decreasing. So this is a work input process. Conversely, with the expansion process, you've got a work output process. Okay. So for the first guy, I've got my work in, I've got a delta U, and one of the assumptions that we are going to assume is that there is no change in kinetic or potential energy. So what that means is that this term right here, which represents the kinetic energy, and this term right here, which represents potential energy, those are going to be 0 for every single one of these processes. So what I've got here is that my work in is equal to delta U. Delta U is what it is after, and I'll put this as, you could put this as M delta little u, right? Big U would be in, say, kilojoules or BTU. Lowercase u would be in kilojoules per kilogram or BTU per pound mass. So delta U would be what it is after minus what it is before. All right, and then our constant volume heat addition process. Let's go back through and just cancel stuff out. So it's a Q in, it's not a Q out. And if it's a constant volume process, we don't have any boundary work. Remember, boundary work is the integral of P dV. So if that dV, the change in volume, is 0, then I don't have any of that. So this and this go away. And all I've got is Qn is equal to delta U, or M delta little u. And that's going to be what it is after. And in this case, what it is after is U3. What it is before is U2. Okay, let's go through it again. So from 3 to 4, isentropic, which means it's adiabatic and reversible, so there's no heat transfer, and it's an expansion process. It's not a work input, it's a work output process. So what you'll notice is that you've got this negative in front of the work out. So our work out is equal to negative. I'm going to redistribute that negative. It's going to be, oops, a negative delta U. Negative M delta U, which would be negative M, what it is after, U4, minus what it is before, U3, or this could be just M times U3 minus U4. Very last one. So this is a constant volume heat addition process. We're going to go through again. Constant volume, which means there's no boundary work, so there's no work input, work output, because there's no change in volume. And then it's a Q out, it's not a Q in. So our Q out, and here we've got that negative sign that's going to be a negative delta U. So negative M times delta U. Delta U is what it is after. In this case, this is a process from 4 to 1. So it's going to be U1 minus U4, or just M times U4 minus U1. All right, so we're going to go through a problem right now, but there are several practice problems available, and those are clickable links. So if you'd like to practice more after we get through this one, you know, there you go. You've got a couple of options there. All right, so we've got an ideal Otto cycle has a compression ratio of 10, and what I've done here, some of the, you know, a lot of time typically is spent writing down in class when we go through all these problems, the given, find, assume. And so what I've done here is I've written that down for you, but just keep in mind that's going to be up to you to do. So I've got an ideal Otto cycle, and just for my own, you know, being able to, well, what do I mean by T1? What is 1, right? I've written down, okay, I'm going to define the 4 processes, 1 to 2, isentropic compression, 2 to 3, yada, yada, yada. Do be aware that on your test, you will need to memorize those 4 processes, okay? So you'll need to know 1 to 2 is an isentropic compression process, that stuff. The only thing that you're going to have is the equations on the equation sheet that's in that big PDF packet. All right, so the temperature and pressure at the beginning of that compression process, so T1 and P1, 17 degrees Celsius and 100 kilopascals. And then it says 1,000 kilojoules per kilogram are added to the cycle. So that's your QN there, and it's a lowercase qm because, right, it's on a per mass basis. And then the compression ratio, which is the maximum volume over the minimum volume, is 10. Well, the maximum volume would be, or the specific volume, right? You could express it on a per mass basis. The maximum volume or specific volume is going to be before the compression, and the minimum is going to be after the compression. So hence the 1 and 2. And then we're supposed to find the thermal efficiency, and we're going to assume both solve it using air standard assumptions and also cold air standard assumptions. So we won't do this all the time, but I do want to show you how you can solve these problems both ways. So on the left-hand side, we're going to use air standard assumptions, which is a little bit more difficult, and cold air standard assumptions on the right, which is a lot easier. So I guess steady state doesn't really matter, but we are ignoring kinetic and potential energy changes. We are also making air standard assumptions on the left, which means that you've got an ideal gas. You don't have any heat transfer where you don't want it to occur, which would be during compression and expansion. There's no irreversibilities. And then with the cold air standard, we're going to add one additional assumption, and that's that we have constant specific heats. And we're going to take that at 300 Kelvin. So K is equal to 1.4, CV is equal to 0.718 kilojoules per kilogram K. Keep in mind, in this class, I think every single problem that I do in class, I take those specific heats at 300 Kelvin. And so your CV is 0.718, your CP is 1.005, K is 1.4. But if you follow along in your book, there are problems in the back of the book that they may tell you to whose K is equal to some other number. So they're taking the specific heats at another value. Okay, so let's go ahead and derive our equation. So you may or may not recall, and actually I'm going to go back, well, yeah, I'm going to go back to the very first thing that we wrote down. So up at the right hand corner, this is that simplified diagram of a power cycle that you may remember from Thermo 1. And you may also remember, hopefully, you may also remember that for a power cycle, you have the performance parameter, which is your thermal efficiency. And it's defined as work net out over Q in. Okay. You may also remember, and if you don't, I would encourage you to review the Thermo 1 Unit 4 playlist. You may also recall that for any thermodynamic cycle, not just power cycles, that work net out is equal to Q net in. And that Q net in is any Q in minus any Q out. So you could put this as 1 minus Q out over Q in. So you've got a couple of different ways of defining that thermal efficiency. And so I'm going to take those equations and remember on your equation sheet, I believe this might be the only one that's written down and defined for you. So it would be up to you to know that for any cycle, your work net out is equal to your Q net in and be able to get this equation right there. All right, so with that being said, let's go back to our problem there. All right, so it is your work net out over your Q in. And that would be any work out minus any work in over your Q in. And we've just defined that stuff up here. So I've got an equation for work in and work out and Q in, and so that's what I'm gonna put things in terms of that. Okay. So I'll put it right here. How about? And I'm going to have a mass multiplied by all these terms, and so you could see that mass is just going to cancel out. So I'll just go ahead and do that. But it's the workout is from 3 to 4. So U3 minus U4, and the work in is from 1 to 2. So U2 minus U1, and then your Q in was from 2 to 3, so it's going to be U3 minus U2. Perfect. So there's our governing equation. So I know that for all of these things, I need to find the internal energy. And this is for air, and really the only thing, well, I'll leave it at that. I have another way of defining that thermal efficiency if I wanted to. So it's also equal to, as I just saw, 1 minus Q out over Q in. And on the previous page, I've figured out what all of those things are. So the Q in is U3 minus U2. And the Q out was from 4 to 1, so it's going to be U4 minus U1. Of course, that mass is going to cancel out. So either one of those are acceptable. You can define it both ways. A good idea would be to, calculate it both ways. And if you get the same answer both ways, you know that probably all those U values are okay. If it's not the same, then you know you've probably messed up somewhere. Okay. All right. So, perfect. Well, if we made cold air standard assumptions, we're assuming that specific heats are constant. So this equation becomes, instead of things in terms of delta U's, well, remember For an ideal gas with constant specific heats, any delta U's can be approximated as CV delta T's. That's on your equation sheet. So this becomes CV times the delta T's. T3 minus T4 minus T2 minus T1. On the bottom, this becomes CV times T3 minus T2. And of course, these CVs just cancel out. Or, if I wanted to use this one, this would become 1 minus, got a CV times T4 minus T1, CV times T3 minus T2. Okay, perfect. Perfect. All right, so let's see. Guess I got to figure out all those temperatures, don't I? Temperatures and internal energy values. All right, so first things first, I'm going to have to rely pretty heavily on those ideal air tables. So 17 degrees, this is 290 Kelvin, and I'm going to put it like that because my ideal air tables are organized in terms of that. So let's go ahead and go to those tables. Perfect. So I am going to the ideal air tables and I am looking right there. So at 290, I can go ahead and get my U value. And then you're also going to note, if you look on your guided notes, you'll see that I also, sure, perfect. I also have a place for VR. So we'll talk about why we need that, but let's go ahead and circle it. And then I'm going to put it on my guided notes here. So at 290 Kelvin, my U value is 206.91. And that's in kilojoules per kilogram. And then that VR1, our relative specific volume, that's going to be, let's see, 676.1. And there's no units there. It is what it is. All right. Doesn't really matter, but 290 Kelvin. Perfect. All right. And on, with cold air standard assumptions, I don't need to pull out any U values. In fact, if you're solving a problem using air standard assumptions, you don't need to touch those ideal air tables at all. You've got everything you need just with the temperatures. That's all you need. All right, so state 2, I need to figure out my U value at state 2. And so what I'm going to do is I'm going to think about how state 1 and state 2 are related to one another. Well, from state 1 to state 2, you have an isentropic compression. So you have an isentropic process for an ideal gas. And remember, I'm going to use our isentropic relationships for an ideal gas. So if you forget where those are, can I make that? Oh, perfect. They're all over here. So if you don't assume specific heats are constant, which is what we're going to be doing for the air standard assumptions, you got to use relative specific volumes, or if it was useful, relative specific pressure or relative pressures. If you assume that specific heats are constant, then you can use those guys over there. Probably we're going to use that guy. Okay, so perfect. Go back over here where we are. Okay. So on the left-hand side, remember this is air standard assumptions. We're not making the assumption specific heats are constant. So I'm going to apply that isentropic relationship. This is equal to V2 over V1, and I happen to know that ratio because if I look up here on my givens, that's oops, not that one. It's this guy right here. That's our compression ratio. Well, the inverse of our compression ratio, rather. So it's 1 over R. So I've got my VR1, and I just solve for my VR2. So this is going to be 67.61. And so where that's going to be useful to me is that our U2 is going to be the internal energy at VR2. So if I go to my ideal air tables, I'm just going to read right off the table. And yes, there's going to be some interpolation involved. So this is state 1. And then state 2 is going to be where my VR value is equal to 60 something. Yeah, right there. So this is going to be VR2. My head's probably in the way, but I've got 67.61. Okay. So I'm going to zoom in there just so we can see what we're talking about. This is, of course, the temperature. This is the internal energy. This is the enthalpy. This is that S naught value. This is the PR value. This is the VR column. So, yeah, we need the corresponding internal energy. So it looks like it's between 724 and change and 734 and change. And so, is that right? Actually up here, isn't it? Oh, I'm so sorry. This one is mixed up. Apologies. This is our H value. This is our internal energy. Actually, I think, just looking at it now, and I'm sorry, 67.61, that would be a little above, wouldn't it? That'd be right there. Okay. So, oh, fine. That pretty? All right. So apologies. That would be between those guys, wouldn't it? So between 512 and change and 520, and I've got 518.64. That looks better. So 518.64. And that's kilojoules per kilogram. So what I'm going to do here is I am going to kind of highlight here we go. I'm going to highlight the stuff that I need for that governing equation. So there's my U1, there's my U2. Really the only thing I needed on the right hand side is the temperature. So perfect. All right. So if I look over here on the right-hand side, still I'd use an isentropic relationship. Or an ideal gas, but this one I could use the one designated for constant specific heats. And there were 3 of them on your equation sheet, but I'm going to use the one that relates the temperature ratio to the specific volume ratio. So this is V1 over V2 to the K minus 1. And so it's just a matter of plugging things in. So this will be R to the K minus 1. So my temperature ends up being 728.45. Perfect. and that is in Kelvin. Make sure that you put the temperature in Kelvin, otherwise that will not work. Go. Okay, back over here. So for the air standard assumption, solving for state 3. So from 2 to 3, we've got a constant volume heat addition process. So it is not an isentropic process because you've got heat addition. So let's write that. It's not an isentropic process from 2 to 3. So what can we use? Well, maybe we can use our ideal gas law if that would help. Or we can also use our first law. And so the first law is actually going to be useful for us here because they actually told us the amount of heat that's added per cycle. And that's the Qn. So this is going to be added from 2 to 3 during that heat addition process. So we already have an equation for that. So if I look on my previous work, well, at Qn, it would be U3 minus U2, wouldn't it? So let's write that down here. U3 minus U2. So my Qn 3 minus U2, which given to us is 1,000 kilojoules per kilogram. So our U3 is just going to be 1,000 plus our U2 value, so 1518.64. All right, perfect. Well, not wanting to do that one. All right, so there's our U3 where we're moving right along, aren't we? All right, if we were able to assume specific heats, it gets even easier because it's the same equation except that our Qn, which is 1,000 kilojoules per kilogram, it's equal to U3 minus U2, but since we're assuming specific heats are constant, it's going to be CV times T3 minus T2. All right, and so our T3, keep in mind you got to divide through by that CV, so don't forget the CV is there, 0.718 kilojoules per kilogram, but our T3 is going to end up being 2121.21. It's 21.21. That is not kilojoules per Kelvin, it's just Kelvin. Perfect. All right. And then our U4. So over on the left-hand side again. So it's an isentropic process from 3 to 4. So we could use our ideal gas law, we could use our first law, or we could use an isentropic relationship. And we would just use the one in terms relationship. We'd use the one that's in terms of those relative specific volumes. So our VR4 over VR3 is equal to V4 over V3. And well, I didn't write down VR3, but I do actually have enough information because I can pull that off. This would be the relative specific volume corresponding to that U3 of 1518.64 kilojoules per kilogram. So let's go look at our ideal air tables and find where that is. So 1518.64. So let's see. Go. Looks like it's going to be right there. So I'm going to zoom in as much as I can without it being confusing. This would be 15, 18, 6, 4. So I'm going to zoom in actually just a little bit more. This is our temperature, this is our enthalpy, this is our internal energy, this is our S0 value, this is our PR, and this is our VR. So corresponding VR value is going to be between 3.944 and 3.601, and I get a value of 3.718. It's okay, 3.718. 3.1 a second. Forgot it. 3.718. Okay, and that's unitless. Okay, perfect. All right, and so we can get our VR. Well, actually, wait a minute. We're kind of skipping ahead, aren't we? Because while I have the compression ratio, V1 over V2, I don't know, maybe I don't know V4 over V3, or maybe I do because, but, oh, ooh, exciting. Because, remember, the process from 4 to 1 is a constant volume process. And the process from 2 to 3 is a constant volume process. And so this just becomes R. So our VR4 is going to be 37.18, right? All right, and so now our U4 is going to be the internal energy corresponding to that VR4. So heading on back to our ideal air tables, 37.18. All right, so I'm looking in that, see where 37 point, here we go. So right here, 37.18. Okay, so right there, so our corresponding U value is going to be between 641 and change and 657 and change. I got a U value of 654.2. 654.2, perfect. And that's going to be kilojoules per kilogram. Oops. And at this point now, if I look back up at my governing equation that I started with, I only need those U values. That's all I need. And so I can plug all that stuff in and get my thermal efficiency. So my thermal efficiency in this case ends up being 55.3%. Perfect. Right. Now, if we could assume that specific heats are constant, same thing. We're going to use an isentropic relationship, but we're just going to use the one for constant specific heats. The one that just has us calculating things in terms of temperature ratio and specific volume ratio. Okay. All right. So same kind of deal, right? I know that the process from 2 to 3 is a constant volume process. So V3 is equal to V2, and from 4 to 1 it's a constant volume process. So V4 and V1 are equal to one another. And so this just becomes 1 over R to the K minus 1. So as long as my temperatures are in absolute temperature units, I'll get the right answer. I've got a T4 of 844.5 Kelvin. All right. So here we go. Oops, like how that looks. There we go. Better. Better. And so if I look back at my governing equation, that governing equation all the way at the top is just in terms of temperature, so that's all I need. So my thermal efficiency ends up being 60.2%. Perfect. Perfect, perfect. And that's it, right? So you can see the one on the right, if we make cold air standard assumptions, it's a lot easier. And you shouldn't have to look at those ideal air tables at all, but it's not as accurate. The 55.3% number is a more accurate number than the 60.2% number. But on a test, I'll be specific about which method that I want you to use, okay? All right, so we have about 14 minutes left, so we're going to go ahead and introduce the concept of diesel power cycles, and that shouldn't say gas. That should not. It's just a diesel power cycle. So this is a diesel power cycle. This is used to model the compression ignition engine or the diesel engine. So the difference here is that combustion, just the mechanism by which combustion happens, or at least from as far as we care, it's just the mechanism by which combustion happens. So you may recall with a gasoline engine, what comes into the cylinder when that intake valve opens is fuel and air. But for a diesel cycle, the only thing that's coming in is air. And the air is compressed to a pressure and a temperature above the auto ignition temperature of the fuel that's going to be injected. And so the third picture that you see with the power stroke here, the thing that initiates the combustion is just the injection of fuel. And because the temperature of that air is above the auto ignition temperature, you'll have the combustion event. It'll force that piston head down. That's where you get your power output from. And then when it comes back up, that's when your combustion products leave through the exhaust valve. Now, our simplified model is our ideal diesel cycle. So we are simplifying things in that, think back to those ideal air assumptions. We are modeling it as our working fluid is air. So we're not worrying about the fuel. We're modeling it just as air, and the combustion and the exhaust are modeled as heat addition and heat rejection processes. So super, super simple model. And once again, don't try to, you might get in trouble if you try to map each four of these processes to each of these actual events here. It doesn't map perfectly. I'll say that. It doesn't map perfectly. All right, so let's go ahead, and you'll notice my first law, if you're looking at the notes that were previously up there, the first law is a little bit different. So just make sure that if you need to, correct that on your own notes. But it is updated on the guided notes that are posted on Canvas now. All right, so for the diesel cycle and these processes, you'll need to memorize as well. And they will look really similar to the Otto cycle. You have an isentropic compression process. And if you'll recall, this was where you'll have a work in, but you won't have anything else, right? You don't have heat transfer or anything like that because it's isentropic. I'm going to skip 2 to 3. Let's come back to this, to that later. Oops. 3 to 4. That's our isentropic expansion process. So no heat transfer, but it's an expansion process. So you do have a work output. And then from 4 to 1, constant volume heat rejection. So in this one, of course, you do end up having a Q out. but you don't have any work associated with that because it's a constant volume process. So all three of those processes are exactly the same as the Otto cycle. So as far as memorization goes, you know, not so bad. But there is a difference between how we're modeling the heat addition, or how we're modeling the combustion process in the diesel versus the Otto cycle. So for the diesel cycle, instead of being a constant volume process, this is going to be a constant pressure heat addition. So learn how to spell addition. That would be good too. So I'm going to go ahead and kind of cut to the chase with these guys. So it's the same derivation as before. This is m times u2 minus u1. This is m times u3 minus u4. This is m times 4 minus u1. All right, but now we got to think about this constant pressure heat addition. Okay, so if I apply my first law, and I've got my first law, and I'm assuming that kinetic and potential energy changes are negligible, so it's a heat addition process, not a heat rejection process. And then I've got this constant pressure process, so it's not constant volume, so my work is not equal to 0. As I add heat, things are going to expand, right? I'm allowing the pressure to be constant, and so I'm not like adding any extra pressure to keep the volume constant. No. So as I add heat, I'm going to have an expansion process, which is a work out process. So this becomes Qn minus, and I've got a work out. So you'll note that you've got a workout process, workout during 2 to 3, and workout from 3 to 4. This is equal to big delta U, or just m delta little u. That's fine. And then this work output, it's boundary work, and we have an equation for that. It's P dV. And it's a constant pressure process, so when I'm evaluating that integral, it's really convenient because the pressure is constant, so the pressure comes out to the integral. So this is P dV delta U. I probably should be making this green to make everything. Okay. Well, so this becomes P delta volume, right? And then of course I can isolate the mass on the outside. This would just become m delta specific volume. And then if I wanted to calculate that Qn, he's going to be m delta U plus m P delta V. So this is delta U plus P delta V, which you may recall is the definition for enthalpy. So this becomes m times delta H between 2 and 3. So it's what it is after minus what it is before. So the big takeaway message is that you do have boundary work that you're going to have to take into consideration there. And so that alters the first law. And then the other takeaway message is that in addition to a heat input, also have a work output. So you got one here and you got one there. Okay, so we got about, what is it, 15. Yeah, so we got 6 minutes left. 5-6 minutes left. There are some additional practice problems if you need some extra practice. Let's look. Yeah. But we're going to go ahead and kind of solve this here together. So this is going to be, we're going to solve using cold air standard assumptions, which means that the specific heat is constant. And if you want to see it solved using air standard assumptions, there is a video online for this as well. All right, so ideal diesel cycle, and I've went ahead and put the processes here, although I don't know where you 2 to 3 went from, what to. So we've got a compression ratio of 18. So same thing, the volume before versus the volume after compression. They give us the temperature, pressure, and volume in the combustion chamber at the beginning of that compression process. So that's all state one there. Okay. And then they also give us what's called the cutoff ratio. So the cutoff ratio is to account for the fact that during that constant pressure heat addition process, do have a change in volume. And so that cutoff ratio accounts for that. So V3 over V2, or you could put it in terms of specific volume as well. V3 over V2, so that's the cutoff ratio. Right. So what I would like to do with the 4 minutes that we have left, I've went ahead and put all of our assumptions over here. So cold air standard assumptions, and sort of, the thing sort of tease out what all those assumptions are. So we want to find the work net out in BTU, and then we also want to find the mean effective pressure. So with the work net out, it's any work out minus any work in. So if we define it like that, we're going to have 2 workout terms, remember, right? We've got the one from 2 to 3 and the one from 3 to 4. So the one from 2 to 3 is P delta V. So that would be P times V3 minus V2. That's the work output from 2 to 3. We also have a work output from 3 to 4, and that's delta big U. So big U3 minus big U4. I could isolate the mass, and that would be fine. And I could put it in terms of little specific volume and little u. And then my work input is from 1 to 2. Once again, I have that defined up there at the top, 2 minus U1. Or I'm going to do I'm going to show you how I am going to do it. So remember, for any cycle, not just a power cycle, not just a gas power cycle, doesn't really matter. Any thermodynamic cycle, your work net out is equal to your Q net in. And the reason I'm doing that is instead of having 3 terms, I'm going to have just 2, because I've got one Q in term and I've got one Q out term. So this is the Q in is from 2 to 3, and the Q out is from 4 to 1. And we have those defined up there. So your Q in is M delta H. So M H3 H2. And then your Q out is from 4 to 1, and you have that defined as well. So it's U4 minus U1. And last thing I'll write, because we are assuming specific heats to be constant, those delta U's and delta H's can be put in terms of CV delta T's and CP delta T's. So delta H, CP delta T. I know it just flipped over. So this is the last thing I'm writing. There we go. And so I've got my first governing equation. You'll notice that I still need to find that mass. Boy, that would be a good job for the ideal gas law. So that's probably what we'll start with the next time, okay? Alrighty, I'm still waiting on my grader to let me know what his office hours are going to be, but I'm asking that he do that either 30 minutes on Tuesday and Thursday, or maybe 1 hour on either one of those days, just to account for the day that I am not doing office hours, okay? So I will see you guys on Friday, and here you go. All right, thank you.